Advan, yes, works, yes. About one notion, this was introduced in 1960s, and many honest schools of data mining and pattern recognition, artificial intelligence explicitly told that they work only when the patterns are compact in Braverman sense. And this is a hidden background. But many people, and this is, I will not criticize them, but you should understand, work by the principle, we work until it works. We push a button, and if the button works, we don't care about anything. This is a tradition, and it will continue until the mountain of errors will become too big or too dangerous. This is absolutely normal, this is absolutely human, but sometimes we should think about some deep background. Today I will tell you about that. So, wow. The goal of machine learning research is not the discovery of a universal learning algorithm or the absolute best learning algorithm. Instead, our goal is to understand what kinds of distributions are relevant to the real world that an AI agent experiences, and what kinds of machine learning algorithms perform well on data drawn from the kinds of data generating distribution we care about. So, and this is Gottfellow Benjamin deep learning. Absolutely similar statement was in the famous book of Wapnick at the end, Experiment Statistical Learning. So the main focus at the end, people who work their whole life in data mining and artificial intelligence, the result is that the main problem is how world is organized. Here, I should recall a very famous sentence of Feynman, Richard Feynman, in his first volume of Feynman Lectures of Physics, told that if the world will be destroyed, he will be asked which one sentence we should keep for the next mankind, for the next civilization. I tell, atoms. Everything consists of atoms. About data mining, I should say, absolutely trivial thing. Our world consists of things. It consists of discrete patterns. And this is our environment. I look on you, I see discrete patterns. I look at tables. Of course, somewhere on the edge of quantum world or waves and so on. But even there, we understand fluid dynamics much better if we found their discrete structure, vortices and so on. We understand quantum physics, solid state, much better if we found their quasi-particles, something like this. And this is, I don't know, to be absolutely philosophical, I don't know where the structure of the world is transferred to the structure of our mind, what we see. But nevertheless, it's our world. Now we have a bunch of problems. We'll work with bunch. This is a bunch of problems. For your pleasure. 3 problems. First problem, one told already many times, AI makes mistake and will make mistake in the future. It's absolutely normal, and these mistakes are different from our mistakes, and we should be ready for them. Then non-classical data devaluate classical statistical learning. It was understood step by step at the end of 20th century, and at the edge of this millennium, David Danocha, a very well-known data analytic from Stanford, in his millennium lecture, where he would try to be a Hilbert. No, he did not tell this, but we understand that he could try to propose a problem, a series of problems for next generations, told that the main problem is that the data are not classic. That therefore, in this new data world, we have no law of large number, we have no central limit theorem, we have no orthogonal basis. We have something different. Of course, under proper conditions, we have law of large number. Under proper conditions, we have central limit theorem. And of course, if you can measure precisely orthogonality by vectors, we have orthonormal basis, but this is not the case in the reality of non-classical data world. We will do a strange thing. We'll utilize problems 2 and 3. Problem 3. Of course, the problem 3 is connected very much to problem 2. The data distribution in the real world are very far from being random. That's Geoffrey Hinton. It's very good to be Geoffrey Hinton. Each sentence he told can be easily, Hinton told. Therefore, but this is more or less clear statement that when we use yes, me too. I asked that. It means that all standard probabilistic assumptions about smooth probability distributions and so on don't work. Therefore, all standard, so are non-random in standard probabilistic, in the sense of the standard application of standard probabilistic tools. Of course, this is some paradoxical form. He's not an idiot, therefore we should try to understand what he told. Of course. Okay, problem 1. No, problem 1 we discussed many times, but let me return to that. AI makes unexpected mistakes and will make them in the future. There were many examples in the previous lectures. Now just one important already, so Wikipedia calls secondary source, not the first reports of mistakes, but secondary sources. It means that in reports of experts of United Nations, of Council of Europe, and so on, and even special database accumulated significant errors, not just short, funny stories, but significant errors. Sorry? Where? It's in chat. Okay. Question and answer. Maybe somebody can help me because it's very difficult. How can we obtain record of this lecture, please? It is very interesting for me. It is not for me question, of course. So, huh? Yes, it should be recorded. Is it? It's recorded. It will be available online. Skolkovo will make this available online. Okay. So, okay, where is my? So, this is the references to secondary sources where these errors are already somehow analyzed, collected, and these are United Nations, Council of Europe, special database, and many others. You can find this, but you should say that you should not already, 7 years ago when we started this, we started to collect because nobody cares so much. Now we should just go to the big sources, to our collection as well. What happens? Something happens during our click on the presentation. Here already. Click. Oops. No? So no, that is. So there was a message one. We already told you is the main 2020s problem of is errors of AI and their processing. And errors is unavailable companion of data-driven AI. And the new AI winter will come. It will come. It's definitely will come if you don't care, if you don't focus on the problem of errors. It will absolutely for sure. It's as it was the first time, it will be the second time, it will be the next time. Of course, somewhere application will survive where errors are not very dangerous. It was already several times. So, can we correct errors? The question is, yes, if you work in low-dimensional world, why not? We have many statistical tools. We can evaluate probability of error. We can find diagnostic tools. We can find easily produce many different, but all of them that are efficient for correction of errors, improving our statistical models, and so on. In low dimension. What does mean low dimension? Interesting question. I say that the border starts near 10 and 100 is already not low. Dimension 100 is already high. Dimension 10, it depends. Dimension 3, from 3 to 2, 3, dimension y, nobody cares. Dimension 2, 3, 5, the classical methods work. Why? Why we cannot work non-classical data, devaluate classical statistical learning? This is, I share with you my impression from a lecture of David Danoha. Why I share? Because, of course, we usually invent some works of classics by ourselves. Then we open he did this 7 years before us. So if you remember famous Ostap Suleiman Berta Maria Benderbey, he created poetry, And then I found that this poetry was written by Pushkin many years ago. So big kick from the classic. Therefore, it's the same. Of course, we understood it independently of Danoka. Danoka formulated in huge lecture. This is in very much detail. First of all, he told that we meet the situation with the number of attributes is much more the number of examples very often. From my practice, I come to doctors. For each patient we have like 1,000. I don't remember how many. Many. We have very big data. You should have in mind wide data. And how many data points do you have? Oh, many, 28. And this is this was real situation. Of course, sometimes there are very nice discoveries in this inverse situation or in situations when the data dimensionality grows proportional to the number of examples. It's also Pastor Leaf, many, we shouldn't discuss details. But in general, this is the area where the classical statistical theory doesn't. This is Danoka. But even Danoka can be criticized. First of all, it's important to compare the number of attributes with a logarithm of the number of samples. Why? Because many analytical estimates work with exponents. The number, or with logarithms, it's the same. Where you put, you should either put here logarithm, you put here exponent. Post-classical world effect begin at long before the Danoka told. This first, the classical world is around. Another correction into another line, another side, is that data dimensionality is not the number of attributes. And we should be very careful. Just a trivial example to have in mind. In our data are distributed along a straight lines without any disputable manifolds or something else, or flexible, how flexible. A straight line. Dimension is 1. It does not matter that there are 10,000 attributes. Dimension is 1, and we don't meet any high dimensional effects in this case. Therefore, dimension of data sets. And therefore, here appears a very strange number, this dimensional finite set. We discussed it in my first lecture. I just make a hint and return to this lecture. I will not discuss it again. Oh, I can, but I prefer to go ahead. There are two. So, Danoka, this is dimensionality, number of points. Classical area is here. Here, all the classical statistical learning theory works. Exponent. Post-classical area is all this big, and the Danoka area is below the bisector. Danoka told, oh, we have terrible area. This is number of n number of examples is smaller than dimension. But if we go to the data dimensionality of data set, the picture slightly changes. First of all, dimensionality of data set is never bigger than n. because we at least should. Yes. Always this is empty area. Then there is post-classical area and classical area. Therefore, this is a final picture we should always have in mind. I don't say this is not, of course, we can put some mathematical theorems below and so on. It's not the most important is clear understanding, the clear understanding that in which world do we work. Okay, how to cope? It's not classical work. And first idea is this idea of a small green frog. One man has asked a small green frog, oh, if you be a big round bull, what will you do? Oh, no. First, I will cut horns. Then I will cut legs. Then I will sit on diet and color myself in green light. After that, I will say, oh, please look, I'm not a big brown bull, I am small green frog. Therefore, we can return to the state of the small green frog and return to classics. I like that Alexandra Gorbaня is here because PCA, I see a principal graphs and manifolds, autoencoders and methods of previous center with some model improvements. These are big collection of methods developed by many good people. Then there is some sort of dual way from data cloud to bigger data, more points, just data augmentation. You should explode, add new points to. I should say that this is the same. This is really the same. The only thing we don't care about the approximant, how we approximate data, but possibility of data augmentations work if and only if there is some hidden possibility to reduce data dimensionality. It's just two dual ways. I prefer explicit approximation. But it doesn't mean that I never use data augmentation. I use data augmentation where I'm lazy or have no time or have no idea how to find the best approximation. But I have in mind that this is the same. And if it works, it means that that's one. There's some methods, there's some books just for you to advertise our own works, by the way. Everything is online. But what to do when the return to classics is impossible? And what we should do? And here we approach the idea of characters. Here I ask you to separate the simplest idea of characters proposed by us, the simplest, which work, from the general idea that is much richer. Characters should be simple, non-change the skills of the legacy, big legacy system, allow fast, non-iterative learning, allow corrections of new mistakes without destroying previous corrections. So we can imagine that there's a huge AI system that made several small errors, and we have to correct these small errors without destroying the huge system and without going to the retraining, because retraining will introduce new errors and so on. This is our program papers here. Well, this is a picture how it works. This initial system is inputs, internal signals, outputs, and characters receives everything. Everything you can receive, or you can already reduce, maybe not all the maybe not all the signals are necessary. And this is a binary classifier that classifies possible situation with high risk of errors from the regular situations where the system worked fine. Then you should equip, we should equip this system with additional decision rule, because for high risk we should act differently, and this is a corrected system. Then that is visualize the problem 2. In high dimension, non-classical data, even simple discriminants are good classifiers. Why? Because this is vacuum, in some sense, and measure concentration phenomena. In high dimension, everything, let's go with, for example, definition of Fisher discriminant. Just separation by linear function. One important notion for everybody who will try. Before all exercises of these characters, do two procedures. First, centralize, and then make whitening. Whitening. It means calculate principal components, kill zero component, and other component renormalize to the same scale, and the covariance matrix will be 1. After that, it works just as inner product. Without whitening, everything is a bit tricky. Not tricky. Whitening is a standard preprocessing. No, this just how it looks like. This in low dimension, extreme points can be inside. Look at put endpoints inside and convex envelope. You can see the extreme points, and many points are not extreme. Extreme points can be separated from other points by definition. And other points are not extreme. Here we have 1, 2, 3, 4, 5 extreme points, and 3 non-extreme. No, just for example. And in high dimension, all points, even with an exponentially large samples, are extreme. Moreover, the second miracle is they can be separated from everything else by the simple discriminant, just orthogonal to the radius, and this distance, cut distance, can be non-small. Usually we select for play 0.2. No, just it doesn't matter. There is no optimal choice a priori. But this can be done by. Why? Because this spheric cap has much smaller volume than the sphere. This is just to explain that this is absolutely non-trivial. This is inside, this is the background of the great discovery of two big scientists, Gibbs and Einstein, who developed in 1902-1903 statistical mechanics. We know Gibbs, Einstein is so great that this small development is he was so big that in 2003, 2005, he developed he developed relativity, he developed statistical mechanics. What? Photons, relativity, and statistics. Brownian motions a bit earlier. But in this first first 5 years was 20th century, and this, no, small. Levy, of course, Levy found this in physical works. He did not cite Gibbs, but the half of this book is about spheres and concentration near spheres. The book where the notion of functional analysis appeared first time. Levy is inventor of functional analysis. And plenty. We started with equidistribution in a ball. Just for example, there are many generalizations. The best generalization is there are many generalizations. I think that the most applied generalizations are covered by convex envelopes of a finite number of log concave distribution. What does mean log concave? It means the logarithm is like parabola by nose up. Log concave means this. Log concave is logarithm is concave function. And this is Gaussian, but not only, of course. Finite number, it means the number that doesn't grow with dimension. Or grows slower than the linear function of dimension. Or something. Or it's a constant bounded by, or a square root of dimension. It doesn't matter. This is, and we don't need the classical idea assumption. It's very general result. Plenty. And then two conditions. No heavy tails, and the sets of small volume shouldn't have very high probability. But very high means exponentially high. Problem 3. Data distribution in real life are very fun for the classical IAD sample from regular distribution. Oh, yeah, just this quotation I like is exactly because paradox. you pay attention. This, of course, in the rigorous sense, this is senseless. That you should understand that. It means that classical probability theory is not applicable. Presumption of sense, the presumption of meaning, because our correspondent was great. So, and now let's go take into account this very important idea of Hinton and go to Braverman compactness. Braverman, this is a picture from Braverman. Braverman told that the images should have something like this. It's good compactness, questionable, and bad. He did not give any formal definition. So just discuss it. Then many people try to define formally. Moreover, in cluster analysis, most of definition of quality of clustering was just formulation, attempt to formalize the Braverman compactness. You say, oh, we create clusters are good. It means they are compact in Braverman sense. There are many attempts to explain people that Braverman compactness is not compactness in the classical sense. After some thinking, I found that this is wrong. If you go to high dimension, Braverman did not think about high dimension, you'll find this Braverman compactness perfectly meets the notion of compactness in infinite dimensional space. What does it mean? In infinite dimensional space, what's compact? Compact can be, in Hilbert space. Let us be not exotic. I can speak about general locally convex spaces, but this is not necessary. In standard Hilbert space, compact can be embedded into ellipsoid, which axis tend to 0, and the number goes to infinity. So this is a sufficiently fast. What does mean sufficient? No, of course, this the question is about the existence of sum of squares for Hilbert space. But this is, for us, this is most important. But this goes to 0, but at infinity, not infinite space, not as a neuter sense, not stops. It's an infinite number. This is approximating ellipsoid, and this is our compact image. Exactly. And this is just small play with definition from the textbook of functional analysis. Nice. Okay, what is compact? It means that the sequence of, nice. Secret. What? The case of ellipsoid sequence semi-axis decays sufficiently fast. It can be summarized. Hilbert brick, for example, Hilbert brick. Standard example of no, can be considered, yes, but Hilbert brick, when it's embedded in Hilbert space, the sides, the edges decay. Yes, otherwise it will not be in Hilbert space. Because it will diverge and the diagonal will be not there. Look on this, so just an example. What do I have in mind? If you look this here, this is a space of patterns, space of data. This is a pattern cat. This is a pattern dog. Of course, these patterns are not small. We cannot say that two small sets dog, small sets cats, and just easily switch. No, they're not small. But in some sense, we can guess that the diameters decay. And Ivan corrected me, not corrected, but let me slightly create dramas, conflict. Corrected me that we should not compulsorily assume that it goes to 0. In finite dimensional case, we should say, oh, it goes to some small epsilon. should not compulsory end by 0, but can end by the epsilon, and then it should have a ball at the end, a sphere, but small. Why not? All the theorems will remain practically the same. But this is maybe important from practical point of view. This is, first of all, logic of patterns. Let us pay attention that the negation of a pattern is not a pattern, it's not compact. We should slightly care. In the beginning of 20th century, people discussed this negation as very bad procedure, like a very bad procedure and so on. And yes, no cat is not a pattern. Yes?
Different dimensions, yes? So, and they decay.
Yes.
So is it means that when we attract some data, some information, so we define the linear dependence between those axes, so that's why they decay. So what I mean that we attract some information, yes?
Yes, yes, try.
We have high dimensions.
Yes.
So dimensions became sufficiently fast decaying.
Yes.
Is it means that those data that we distribute in different axes generally linearly dependent?
Not precisely. Up to some accuracy, yes, because if some axes are very small, then we can just throw them away. This is, we can reduce. And this is exactly what principal component analysis does. But this can be too late. It depends when, how many axes, how many vectors we should keep. It's special logic, it's special. Yes, of course. In some sense, compacts are almost finite dimension. And this is indeed a fact of functional analysis. Compacts are not compulsory finite dimension, of course. But in that sense, we say, with any accuracy, they can be considered as a finite dimensional sets up to this accuracy. But you decay accuracy, dimension grows. And so, did I answer your question? Okay. So this is very tricky question. When we start discuss logic and patterns, consider patterns as events and so on, we find that negation is not a pattern. Negation is not a compact. Even in a bounded sphere is not compact in infinite dimension. Therefore, no cats bounded but not compact. This is just idea. Of course, what else? Oh, and this is a theorem. It explains our interest to that. What is the theorem? Please read. X and Y compact subsets of an infinite dimensional Banach space. And for every epsilon positive, there is such a subspace of directions L of finite codimensions, according to the equation, that for each Z from this S, if the norm of Z is more than epsilon, the shift does not intersect. Yes, and this is a theorem about separation of compacts. And this theorem somehow explains us many issues of adversarial learning. Ivan told us about the critical directions of the adversarial. Here they are. These are critical directions. Of course, they are not thick, they're thin, but thin doesn't mean small. Infinite, S is infinite dimension as well, but finite codimension. It's exactly the, you can exactly use this, you use this theorem in your book. So, in some sense, my mathematical content is a philosophical. I just follow the great idea of Braverman. There were no much, well, of course, there were some theories, but they're not very important from my point of view. Of course, I may be wrong. They're very simple. But what we see, this is a borrowing of Sobolev. I like my teaching functional analysis. Sergei Sobolev invented the idea of compact embedding. He told, we have two, no, he considered two functional space, and a sphere in one space can be a compact in another space. And this can be very useful because it's a way how to prove existence theorems, because convergence in compact sets is trivial and so on. Here we have some universe. For example, we had this universe, just things on the street. We worked with Ivan mostly, but me just through Ivan and other and younger collaborators, but at the same time work with the streets and with this movie, video stream of pedestrians and cars and shops. No, just postdoc walked and TV, camera, to prepare drone, automatic drive at the end. And this we found that there are many different objects. People or somebody is close to people. Cars, bicycles, houses, and so on. But when we go, let us delete cars, let us delete bicycles. Let's go with, it's recognized as people. Then we find there are people, there are men, women, old men. There are hydrants suddenly inside. There are mannequins. So this is quasi-people. We separated this is go to one thing. After that, in this field, we have no cars. Cars remain outside our new world. Let us state people again. Here we take again children, adults. Let's separate adult from children. And so take just people. People are different and so on. And after whitening, compact becomes non-compact because we divide on axis. What is whitening? Yes, this in whitening, this ellipsoid becomes a ball because we took this axis and divided them. This is new metric, new norm. And inside this new metric, we have new universe, and so go ahead, and ahead. This is, I should call this is Braverman structure, and we live in this world. We really live and work in this world. And then, yes, please. No patterns. There will be. No, just no, I don't think so. No, just unique object. We found the unique object. That's all. And this is, of course, if you find the one hydrant. Every time.
Every time when we do the whitening, we destroy the compactness of the of this brown thing. So like that whole brown thing becomes exactly, it becomes a ball. So like it's no longer compact in that new metric. So and then within that new universe, there will be some compact objects which make sense to us, and then we isolate them, and then we carry on. So my question is, do you expect the point where in the universe there will be
not infinite?
Exactly. So like there will be a new universe in which any compact there will be meaningless for us.
Oh, yes, it's absolutely possible.
Yes.
I already prepared to answer. I can prepare. Imagine that you are a small child.
Yes.
Can you imagine?
No.
Or your dog.
That's difficult.
Then you see, you find that this hydrants, and in your hydrants world there is no object.
Yes.
But for your dog, these hydrants will be different patterns, different. You see?
Yes. Okay.
And then for children, some, or maybe for artists, some effects of coloring and so on. Maybe they may become different, but not for you.
Yeah, so like, and I was actually getting to the next point. So once we find this point, like this stage where all compacts in that new universe are meaningless, have we reached the point of, learning or like whatever sense? Well, because like, remember there was this Smail's question about the limit of intelligence. So like, I'm kind of
I should say that this is problem dependent.
Yes.
It's a perception, my paper about children and adulthood.
Yes.
Because from order and disorder notion depends on and what is disorder for parents is absolute order for children. Because each toy has its own place.
Yes.
Yes. This is the same here. So for us, if you prepare drones, for us, teeny difference between hydrants is negligible. But if you just play, or we are artists, I don't know why, what for. Then hydrants are even if you just look for the hydrants.
All right.
Because they're old and new, good, or and so on. It depends on the problem.
Okay, fine. Thank you.
So of course it's always. So this chain is always fine, but potentially infinite. But like your contract in King's College, open-end contract, open-end chain is not finite. It's not infinite, but open-end. Yes, there's open-end chain. Do you agree with me? Do you accept this notion? Yes. We can case open-end sequence. One more notion. Stochastic separation are valid for granular distribution. Now we approach new inequality from classical world. Logarithm not on die points, not logarithm number of clusters. Of course, here, in each universe, in each universe, in each stage of this chain of universes, we can see we have number of clusters and dimension of the data set. And the number of clusters, logarithm should be less than dimension. It's almost always. Okay. Now this is a very practical issue. We discuss, one character, 3 characters, 4 characters. Really, we should work we should work as a factory. This is a factory. Characters, individual characters work with clusters of atoms. Each error goes to the closest character. Characters, for example, like imagine there are k-means, k and n, to the closest center. There are many other use the tools, but practically the same. This dispatcher, it selects the closest character to the data. And then character decides, is it possible error? Is it high risk or not? Then it adds, if it is high risk or if it's error, it adds the new error to its cluster and modifies its cluster model. This multi-character can work. It can work not only as a character, but also as a learning algorithm for few shot learning. Now the example of few shot learning. Multi-character in the problem phase detection. We have the problem phase detection. No, so the number of clusters. No, this is correction. This is correction. Sorry. Training, so you see, of course, this curve becomes better when the number of clusters grows. Not a miracle. And this correction of errors, false positive, true positive. This is a standard curve. And this is, I started to speak without looking at the slide. This is more interesting. We have a legacy system who's trained with 9 classes. And then multi-character should recognize the 10th class. Because you can see that we have 9 classes, then we add 1 more class, and there are mistakes. No, from the class was empty at the beginning. But every time when we recognize this new class as some old class is a mistake, and this character should correct this. Very quickly, the multi-character was trained to recognize the new class, the recognition system. For here, but our goal is to understand what kinds of distribution are relevant to the real world. In the infinite dimensional, the Braverman compactness turns into topological compactness. In the granular world, multi-characters give a method for choice for correcting errors. And there are stochastic separation theorems for separation of class. Just one small comment. Why is slightly difficult? See, points, when it creates stochastic separation theorem for sets of points, separate one point from other. The point has no sizes. You can just cut. In stochastic separation theorems for clusters are compact. but some sizes can be huge. Therefore, we should not cut just simple cutting. And this is one difficulty. It was resolved. We can do it. It is, huh? Yes, there's a orthogonal direction. So, but because we have many, if we have many clusters, we should. No, this is. But there are straightforward estimates. How far can we go in this direction? And it works. Slightly more, slightly longer. There's also measure concentration theorems, but not as direct use. And the final slide, please see. It's alarm. Alarm. Bim, bam, bim, bam, bim, bam, bim, bam. Please work, analyze how to cope with AI errors, how to process AI errors. And this is our, I should say, this is our mission. Because new algorithms are not necessary, it's just special race, business race, reputation race, and so on. But mankind can survive without new algorithms easily. But the fighting with errors, the two-phase. First of all, it's fighting for people, therefore fighting for artificial intelligence. Because without fighting against errors, it will die. This baby will die, or will be just very ill, as it was. By the way, because we have some. No, we have no means. Just a story about the first AI winter. The first AI winter, people found that Minsky was guilty. Rosenblatt invented so good neural networks, and Minsky published a book that a perceptron can do not everything. Everything in this paragraph is wrong. First of all, Minsky theorem is not about impossibility of, first of all, Rosenblatt perceptron is a tree-level system that can do everything. And the first Rosenblatt theorem says that the Rosenblatt elementary perceptron can solve any problem. Theorem 1. But of course, therefore, in hidden layer, the hidden layer should be enough randomly selected A elements, but as a whole system, it maybe not the best way. At the end, you can kill non-necessary hidden neurons, but this is Rosenblatt. So, Minsky never told that perceptron cannot solve any problem. He told, logic was, in Rosenblatt elementary perceptron, the inputs of the hidden layer elements were not bounded. They can have as many inputs as possible, or if they work with geometry, they can have as large radius of inputs as possible, and so on. This unbounded. And Minsky said, no, this is too difficult. Let's consider bounded. For example, elements will have either bounded number of inputs or bounded area that collects data, and immediately, without absolutely obvious result, I can explain it in 2 minutes, sometime. It's published in several works, several people. This bounded restricted perceptron has restricted abilities. Unrestricted perceptron is omnipotent, has unrestricted abilities. Restricted perceptron has restricted abilities. Miracle? No. Pathetic, a bit too pathetic. It was just published Why there was some discussion with some sort of because Minsky and Rosenblatt were some time ago at school children in physical-mathematical school in Bronx in the same class. There was competition from the beginning. Yes, I don't know whether they were friends or foes, I don't know, but there was a competition between them in Bronx. And Rosenblatt unfortunately died. And what was the reason, real reason of catastrophe? Real reason was no results. No results. They promised many practical results, and the practical results were not as good as promised. The system made terrible mistakes, and the businessmen stopped funding, and the government stopped funding. And at the same time, because it was a book with some critics, they say, oh, we see this is some critics. With great people like Minsky. No. Minsky is not guilty. He's great. He was. Unfortunately, he also was. Rosenblatt was great, and Minsky was great. Both worked with perceptron. Minsky worked with perceptron. Started simultaneously with Rosenblatt. It was very interesting story. But the story is not about how Minsky killed Rosenblatt project. No. Okay, my friends. But this is those applications. If we don't resolve the problem of errors, then only those applications will survive where errors are not dangerous. That's all. And this is, I hope that idea of Braverman compactness should explicitly help us. Braverman was a great person, genius. He died very, did you know Braverman? No. I know well Rezanov lived, but Braverman died very early. So this is died young person. But Maxim Braverman, his son, is a good mathematician in Boston. Thank you. This is the end of the course. And there will be, after that, there will be separate talks once a week. And the next talk perhaps will be next Friday in a week. And it will be about singularity of transition processes and bifurcation of attractors with applications to artificial and biological brain. This is absolutely different direction. Dynamical system with AI and biology applications. Thank you.